like to talk to you about chiller performance. Most of you are not in the HVAC industry, and I am not either. So let's start by defining a chiller. Chillers supply cold water to buildings for air conditioning and manufacturing. Water goes out cold, comes back warm. And then to remove the heat, they send water to cooling towers, which goes out warm and comes back colder. In the middle is a chiller, which facilitates the heat exchange. I'd like to thank Optimum Energy, which is a local Seattle company, for inspiring this project as well as providing the data set. Chiller manufacturers do provide characteristics when they sell a chiller. They often end up in a back room somewhere and ignored by the operators when they actually are operating the plant. Optimum Energy is in a unique position for collecting chiller plant data as they optimize plants, although at this time they do not use machine learning. So I started with the data set. I had 6 plants, which contained all York YK chillers, so very similar. They ranged in size from 850 to almost 2,000 tons. A ton being a unit of refrigeration. It goes back to the days when refrigeration meant ice. I ended up with 30 distinct but similar chillers in 8 different configurations. I used linear regression to look at a single chiller, so just one chiller, and looking at their performance curves, which is what you see here. On the x-axis is the load. This is the fraction of the maximum power that the chiller can output. On the y-axis is by target. That's the cost per ton. The desires have a lowest cost per ton. Each of the lines are a delta T. This is how hard the chiller needs to work. What temperature difference is it trying to impose on that chiller? What you see, each of these lines is a quadratic in load, and it varies with delta T. A through F being the constants for my linear regression. What I really want to do is predict these constants based on the chiller characteristics. So I combined all my data into a single data set and then added these characteristics of the chillers. Using linear regression, again, I was able to predict these constants. I also used a Bayesian hierarchical model, although I was only able to get the single chiller, and it remains for future work to expand that to the chiller characteristics. So what we have here are some results. These are 2 different 900-ton chillers. Each of the bands represents a 10-degree band of delta T. And when I lay on top the actual chiller data, you can see how that the model is predicting what's happening in that chiller. So how can we use this? Say we have a plant with 4 different chillers, and we have a requirement for 2,400 tons of cooling, 30 degrees delta T. And the desire is to run this at the lowest cost. Back to my chiller operators who know very little about the efficiency. I might just divide the tonnage equally amongst the 4 chillers. However, we do know the performance curves now, and this is how I would operate the plant, with most of the load going to the 1,200-ton chillers, saving about $12,000 a year. So given the data, I am able to predict the chiller characteristics and then operate my plant much more intelligently. And this is true of many complex systems, where given some model of the system, you can make much more intelligent decisions regarding that.